Okay, now we are going to cover doping of semiconductors. And when we are talking about doping, we are not talking about drugs, we are talking about crystal doping. Drugs are not good, crystal doping is good. So, as already told you that undoped silicon does have a certain carrier concentration at room temperature, and that carrier concentration is called the intrinsic carrier concentration. And I told you that for silicon, that intrinsic carrier concentration is 1 into 10 to the power of 10 per centimeter cube. But for semiconductor device applications, for example, for diodes or for light emitting diodes or for solar cells, or as a matter of fact, for photodetectors, lasers, etc., for other kind of devices, this intrinsic carrier concentration is not enough to achieve higher performance from those kind of devices. You would like to have higher carrier concentration for silicon or for other kind of semiconductors so that you can achieve higher performance. So for that purpose, we modify the crystal in a way to increase the carrier concentration, and this method of modification is called the doping of the crystal. Concept of donors, for example, consider the same crystal lattice for the silicon atoms, but now we have added a pentavalent atom into the crystal lattice. One example of a pentavalent, by pentavalent I mean an atom which has 5 valence electrons. For example, the atomic number of phosphorus is 15, which means it has 5 electrons in its outermost shell. So this filled red circle represents phosphorus atoms. It has 5 valence electrons. It's going to share 4 out of these 5 valence electrons with its neighboring silicon atoms. So now the bonding requirement for the phosphorus atoms is fulfilled, and now it still has an additional electron, and with the slightest amount of energy, this additional electron would be free to move inside the crystal lattice. As you can see over here, it's going to move around inside the crystal lattice. In terms of band gap representation, what happens is that as I already told you, the semiconductor, in this case, assume it's silicon, and the dopants are phosphorus. Silicon has a valence band and it has a conduction band, and by adding donors or phosphorus atoms, let's talk about 0 Kelvin, it means that we have introduced donor levels close to the conduction band of the semiconductor at this point. But still, at 0 Kelvin, all the donor electrons would be bound to their native atom, which is phosphorus in this case. We still need a slight amount of energy so that these electrons can jump from the donor levels to the conduction band. So if we increase the temperature slightly, some of the electrons would move from the donor level to the conduction level. And at room temperature, all the electrons would move from the donor levels to the conduction band, which means now we have a lot of electrons available for conduction from the n-type doped semiconductor. Concept of acceptors, which means adding extra holes. Now, in order to add extra holes into the semiconductor, we need a trivalent atom. Examples of trivalent atoms are boron, aluminum, indium. The atomic number of boron is 5, which means it has 2 electrons in its first shell and 3 electrons in its valence shell or outermost shell. So 3 electrons of this boron atom, which is represented by the filled yellow circle, would be shared with the adjacent silicon atoms, but in the fourth direction there would be a missing link, a missing bond, an absence of electron over here to fulfill the bonding requirement in this direction as well. And whenever we have a missing electron in a crystal, the absence of electron is called a hole. So over here it's going to introduce a hole. One less bond means the acceptor is electrically satisfied. It would result in an acceptor. And one less atom also means that the neighboring silicon atom is left with an empty state. So basically we have an absence of electron over here, which means we have introduced a hole into the crystal lattice. Now, why is the concept of hole also important? Because here we don't have a link, a bond over here. So what happens is, over time, this electron from the neighboring atom would jump from this bond to this missing link. As you can see it over here, it has jumped from here to this location. So now the bonding requirement over here is fulfilled, but we have a hole left at this spot. And further, what happens is another electron from over here would jump into this location, fulfilling the bonding requirement over here, but then we have an absence of electron at this spot. And similarly, another electron would jump from here into this previous part, but then the hole keeps moving to another adjacent silicon atom. So which means that effectively the hole is moving towards the right and the electron is moving towards the left. And what do we need in semiconductors for conduction? We need carriers to move around inside the crystal. If carriers are moving around inside the crystal lattice, it means that it's going to result in conduction or current for us. And that is important. That is what we need. So basically, adding acceptor means the addition of an acceptor level close to the valence band of the semiconductor. These are acceptor levels close to the valence band of the semiconductor. And the valence band we need, there are plenty of electrons always available inside the valence band. So at absolute 0 Kelvin, the electrons in the valence band are still intact. They have not jumped to these acceptor levels. But if we slightly increase the temperature, electrons from the valence band would jump to these acceptor states, acceptor levels, leaving behind holes in the valence band. And at room temperature, most of the acceptor states would be occupied by electrons jumping from the valence band to these acceptor levels. And because of that, now we have room for inside the crystal lattice for carriers to move around and result in current. I also want to, so basically in this lecture I'm covering some preliminary concepts, and I also want to cover the growth of semiconductor materials. And there are basically two techniques for growth. One is growth from melt, and another one is epitaxial growth. Have you seen silicon wafer? I'm not sure, but actually at our center we have silicon wafers in this form. So this is basically a silicon wafer, and if you visit the center, at some point I'm going to show you how a silicon wafer looks like in reality. So the point is, how do we achieve silicon wafer, or how do we achieve crystalline silicon? The process involves going to the beach and grabbing sand. What is sand? Silicon dioxide. And then after some chemical reactions, it would result in metallic silicon, which is another grading level of silicon. But we need to further purify even this metallic grade silicon. So after further chemical processes and some heat treatments, we would get silicon in the form of these chunks, in the form of these grains. And this is called pure polysilicon, which is 99 point, these are I think 11 nines. So 11 in purity material. But this, it's still polycrystalline silicon. And as I already told you that polycrystalline material has grains, it has ordered arrangement of atoms in regions, but it doesn't have periodic arrangement of atoms throughout the entire crystal lattice. So if you still want to achieve single crystalline material, periodic arrangement of silicon atoms throughout the entire crystal lattice, you need to pass it through another process, which is called Czochralski's method, or another method for that would be float zone technique, in order to achieve single crystalline silicon. And then and this is called a bowl, and then you slice the bowl into circular wafers. Here is the Chokrelsky's method for growth of silicon from the melt. So you take these granular form silicon, you place it in a crucible, you heat the crucible, which is going to melt down silicon, and this process would occur above 1200 degrees C at a really high temperature. And then you introduce a single crystalline silicon seed into this tube, which kind of looks like a flask. It has a narrow neck, and you keep pulling up the seed from the melt, and you also rotate this infrastructure at the same time. So by rotating and pulling it up at a slow pace from the melt, it results in periodic arrangement of atoms in a single crystalline boules, and this is the end product, which is kind of an upside version of what is happening over here. And basically it results in different diameter wafers. We have 2-inch diameter wafer, 4 inches. The maximum achieved so far is approximately 18 inches diameter wafers. Epitaxial growth. Epitaxy means layer by layer growth of materials, of single crystal materials. And epitaxy could be homoepitaxy. For example, you can have a silicon wafer and you want to deposit silicon on top of that silicon wafer. This is called homoepitaxy. Or it could be heteroepitaxy. In heteroepitaxy, you might have silicon wafer and you might like to grow gallium nitride on top of that. Or you might have sapphire and you want to grow gallium nitride on top of that. Or you might like to grow silicon on top of gallium arsenide. So it's growing different kind of materials on top of each other. It's called heteroepitaxy. And for both homoepitaxy and heteroepitaxy, there are different growth techniques. Chemical vapor deposition, liquid phase epitaxy, and molecular beam epitaxy. And each of these growth techniques have their own dynamics. For example, chemical vapor deposition involves a substrate. For example, if you want to grow silicon on top of gallium arsenide, so you place the gallium arsenide substrate inside this chamber and you introduce reactant gases, silicon tetrachloride plus hydrogen, into this chamber, and these gases react at the top of the substrate at high temperature and high pressure, resulting in the growth of silicon on top of the substrate. Now this kind of technique, the advanced version of this technique is called metal organic chemical vapor deposition. This technique has certain advantages and it does have certain disadvantages as well. One of the advantages is that it's good for production. For example, most of the LED structures, the blue LED structure, particularly gallium nitride based, indium gallium nitride based, are actually fabricated using metal organic chemical vapor deposition. But the disadvantage of this technique is that it does have a lot of safety consideration. It's not really safe. It doesn't have a safe environment. It has a toxic environment. So there are a lot of safety requirements for this kind of growth technique. Another kind of growth technique is called liquid phase epitaxy, in which you have, this is your substrate, and you want to deposit another material on top of the substrate, so you actually put that material into a solution and heat it up, and you immerse this substrate into this solution and keep it rotating, and at the same time pulling it up and also cooling down the temperature of the melt at a slow pace gradually. So it results in deposition of that material on top of your substrate. We can achieve high quality compound semiconductors using this technique, but it's difficult to monitor. Another kind of technique is called molecular beam epitaxy. It's an exciting technique. It's a physical vapor deposition technique. By physical vapor deposition, we mean that individual atoms are evaporated and they get deposited on top of your substrate. For example, You might like to deposit silicon on top of another substrate, consider gallium arsenide. So what you do is you put your gallium arsenide wafer over here, and you keep rotating this gallium arsenide substrate with the help of a gearing mechanism. And this has an ultra high vacuum environment. The vacuum inside this chamber is more than 1,000,000,000 times lower as compared to the room pressure. And then you have your silicon material that you want to deposit on top of the wafer inside these effusion cells. You heat up the cell to a particular temperature. For silicon, you might like to heat it up above 1200 degrees C. And the silicon gets evaporated because of the high pressure, high temperature, and gets deposited on top of the substrate. So that's how you grow silicon. And it could be used for growing a lot of other materials, for example, gallium nitride, aluminum nitride, indium nitride, ternary alloys, and a lot of other stuff. The advantage of this technique is that it has precise growth control. Like it has a precision of nanometer scale. You can grow really fine, thin layers using this technique, and you can reproduce them every time. The disadvantage is that it has a slow growth rate. Used for gallium arsenide, gallium nitride, a lot of other stuff, especially used for growing indium gallium nitride, because you might like to grow indium gallium nitride at low temperature. I personally worked on molecular beam epitaxy at Georgia Institute of Technology, USA, and it's a complicated tool. It requires like 6 months of training just to be able to grow using different kind of materials inside this machine. So at this point, I want to give you a preview of what is coming up. So in today's lecture, in previous lecture, and also in today's lecture, we tried to cover miscellaneous basic concepts. But from this point onwards, or from next lecture onwards, we are going to cover different kind of devices, starting with p-n junction diodes. So the mechanism or the methodology of this course would be we will cover p-n junction diodes, the theory part, and after covering the theory part in a couple of lectures, I'm going to simulate p-n junction diodes for you, silicon based p-n junction diodes, and gallium nitride based p-n junction diodes, and gallium arsenide based p-n junction diodes. So I'm going to simulate diodes for you by using an exciting tool which is called Silvaco TCAD. Silvaco TCAD basically has the main modules are Athena and Atlas. Athena actually simulates the process TCAD for you, like how do you grow different layers of device. So Athena simulates that, but we will not deal with Athena. We will deal with Atlas, which simulates device TCAD for you. For example, if you have a p-n junction diode, you just define what kind of material you are going to use. For example, you are going to use silicon or gallium nitride or gallium arsenide. Then if it is a p-n junction diodes, what is the donor level in what is the hole concentration in the p-type layer, and what is the electron concentration in the n-type layer. So you define that, and then you apply a voltage to the device structure, and you measure the currents, and you can also look at the energy band diagram of different kind of devices. So Atlas basically models the device operation, and the analogy could be given like Silvaco TCAD is analogous to a virtual fabrication lab in which Athena fabricates the devices and Atlas measures the performance of these devices. Atlas measures electrical performance of the devices, thermal performance of the devices, electrical, thermal, and optical performance of the devices for you. So it's not a complicated tool. It's a really simple and straightforward tool. A good skill for you to learn, because towards the end of the semester you should be able to simulate different kind of devices, and it's a good tool for you. So potentially in the future, if you want to pursue a pursue a PhD position, and if you have a good skill, it's a good addition towards your resume, and you would have higher chances of getting hired by a good professor, especially internationally. And using Silvaco TCAD, I don't want to show you the remaining slides as for now, because here I've introduced LED, but before simulating the LED structure, you need to understand the theory of the LED. So what I want you to know is, we will study the theory of PN junction diode, and when we finish the theory, we are going to simulate PN junction diode, and then we will study the theory of Schottky diode, and we'll simulate Schottky diodes, and then we'll study photodetectors, and we will simulate photodetectors, then LED and simulation of LED, and finally solar cell and the simulation of solar cell. So an exciting, straightforward course for all of you, and I hope we will have a fun time in this course. That kind of concludes the lecture. Do you have any queries for me?
No, sir.
All right. So if you don't have any queries for me, we will conclude the lecture. I'm going to save the videos of the lecture. Once again, if you need it at a later point, you can always get it copied from me, or whenever the Google Classroom is formed, I'm going to upload them on the Google Classroom as well. So as for now, take care, and Allah Hafiz.
Allah Hafiz, sir.